The nebular hypothesis is the most widely accepted model in the field of cosmogony to explain the formation and evolution of the Solar System, as well as other planetary systems. It suggests the Solar System is formed from gas and dust orbiting the Sun which clumped up together to form the planets. The theory was developed by Immanuel Kant and published in his Universal Natural History and Theory of the Heavens, 1755. And then modified in 1796 by Pierre Laplace. Originally applied to the Solar System, the process of planetary system formation is now thought to be at work throughout the universe. The widely accepted modern variant of the nebular theory is the Solar Nebular Disk Model, SNDM, or Solar Nebular Model. It offered explanations for a variety of properties of the Solar System, including the nearly circular and coplanar orbits of the planets, and their motion in the same direction as the Sun's rotation. Some elements of the original nebular theory are echoed in modern theories of planetary formation, but most elements have been superseded. According to the nebular theory, stars form in massive and dense clouds of molecular hydrogen, giant molecular clouds, GMC. These clouds are gravitationally unstable, and matter coalesces within them to smaller denser clumps, which then rotate, collapse, and form stars. Star formation is a complex process, which always produces a gaseous protoplanetary disk, propellant, around the young star. This may give birth to planets in certain circumstances, which are not well known. Thus the formation of planetary systems is thought to be a natural result of star formation. A Sun-like star usually takes approximately 1 million years to form, with the protoplanetary disk evolving into a planetary system over the next 10 to 100 million years. The protoplanetary disk is an accretion disk that feeds the central star. Initially very hot, the disk later cools in what is known as the T-Tauri star stage. Here, formation of small dust grains made of rocks and ice is possible. The grains eventually may coagulate into kilometer-sized planetesimals. If the disk is massive enough, the runaway accretions begin, resulting in the rapid, 100,000 to 300,000 years, formation of Moon to Mars-sized planetary embryos. Near the star, the planetary embryos go through a stage of violent mergers, producing a few terrestrial planets. The last stage takes approximately 100 million to a billion years. The formation of giant planets is a more complicated process. It is thought to occur beyond the frost line, where planetary embryos mainly are made of various types of ice. As a result, they are several times more massive than in the inner part of the protoplanetary disk. What follows after the embryo formation is not completely clear. Some embryos appear to continue to grow, and eventually reach 5 to 10 Earth masses, the threshold value, which is necessary to begin accretion of the hydrogen-helium gas from the disk. The accumulation of gas by the core is initially a slow process, which continues for several million years, but after the forming protoplanet reaches about 30 Earth masses, mirth, it accelerates and proceeds in a runaway manner. Jupiter and Saturn-like planets are thought to accumulate the bulk of their mass during only 10,000 years. The accretion stops when the gas is exhausted. The formed planets can migrate over long distances during or after their formation. Ice giants such as Uranus and Neptune are thought to be failed cores, which formed too late when the disk had almost disappeared.